So strength, how far it disassociates, and this is a key point. That's why they have it bold, okay? The stronger an acid, the weaker its conjugate base. Generally, this is associated with your Ka or Kb. The greater that value is, the more it's going to disassociate. So here are some examples of our strong acids. And you can see that these are, fairly large. Oh, these are like massively large numbers. And then, these are still pretty decently sized ones. Now, remember that this sulfuric acid, that this is a polyprotic, meaning that it has two hydrogens here. The first hydrogen that's coming off is the one that's considered strong. The second hydrogen coming off is a weak acid. Okay? So, when we're talking about chloric acid, that's HClO3, it's often considered to be a strong acid. So if you go to college, your professor might throw that one in as well. AP, this is the ones that they want you to have memorized. Okay, and I've told you about those back in, I think, like Unit 3 or 4. I can't remember which one it was. But I told you a long time ago that you needed to have these memorized. Okay? So, when we're looking at this, and we're talking in terms of a weak acid or base, they're not going to disassociate completely in the solution. That's why we have the two-way error. Okay? We also have things called binary acids. So with binary acids, that just means that we have one hydrogen and we have our anion. So there's two things there, as opposed to a tertiary acid like we would have up here with sulfuric acid. Okay, it's just another way of saying monoprotic instead of polyprotic. Yeah.
If there's like a strong acid and a strong base, does the arrow go both ways?
No, it's going to go one way because they're going to fully disassociate both, and they're going to form water. It's actually a neutralization reaction. When you have a strong acid, strong base reaction, it's called a neutralization reaction. That's why in your, oh shoot, I haven't turned this on yet. In your first year chemistry, I had you do this reaction. And every year when we get to the end and I have you clean this stuff out, people are like, well, can I touch the stuff to be able to, and I'm like, to get that bead out, the stirring bead? And I'm like, yeah, you just made salt water because that's what they made, So it's a neutral. So when you do this, you've created water. And then remember that this is a neutral salt. So you've created literally salt water when you get done with that reaction. Okay. So, but when we're talking about weak, again, that arrow is going to go both directions. Okay. So these binary acids then are created, and typically it's with these halogens because that's why you've only got one hydrogen here because the anion has a -1 charge. The chemical structure then is going to kind of give you an idea of their relative strengths. So as you go along here, you can see that is the acid is getting stronger and stronger as you move along because it's easier to pull away this iodine than it is the bromine. And this goes back to Coulomb's law. We're cycling back around, guys. Okay? Because these things, as you move across here, they're getting bigger, aren't they? So the attraction to the nucleus is getting further away. Increase distance, decrease attraction. And so because of that, it's easier to pull or disassociate HI than it would be HF. And that's why this is a weak acid and these are strong acids. And it all comes back to Coulomb's law. Okay, I'm waiting. Tell me what to talk about. Hydrofluoric acid is not a strong acid. It's weak.
I got confused with the PK.
Oh, yeah. You can actually have negative pKa's, just like you can have negative pHs. If the thing disassociates enough, or your hydrogen ion concentration is high enough, you can have negative pHs. Just like you can have pHs that are greater than 14 for really, really strong bases. Yeah.
Does that mean it's like super saturated?
It means that everything, absolutely everything came apart. The hydrogen's not holding on to any anions.
But it can't negative ones be like -2, -1.
Are you talking about pH or are you talking about concentration?
Wait, what? It can happen with concentration?
Well, your concentrations, no, you wouldn't have a negative concentration, but you would have times 10 to the negative whatever. Okay. Now, if you take this here, okay, and you do 10 to the negative 9.3, you're going to get 2.0 times 10 to the
Wait, Joseph Smith wrote the book of Mormon. So he just like who's like the prophet, right? Okay. Yeah.
So this is how much this guy is going to disassociate. This would be your hydrogen ion concentration in that substance. So that hydrogen ion is going to come apart from virtually everything. I mean, this is a stupid big number, you guys. Okay. All right. So again, you're coming back to Coulomb's law. Okay. We also have these things called oxyacids. So oxyacids have oxygen in them. Okay. And as we are adding more of these oxygens, they are going to be pulling those electrons towards the oxygen in because there's more oxygen and holding it over there. And then that's easier to cleave off that hydrogen and pull it off. So as you're adding more oxygens, this section over here is going to become negative, more negative, even more negative. And by the time you get here, it's way big. And so it's easy for that hydrogen to come off of there. Does that make sense? Okay. So those additional oxygens are going to make that easier to come off. Other effects then, if we have a ternary acid where we've got like 3 things going on, then we can end up with the chlorine being more electronegative. And so as we move down here, this is going to be more electronegative. So electronegativity of X. So our X is here. So as we are increasing the strength, the electronegative elements are included in the structure, and we're getting more acidic because we're moving further away from that, from the nucleus. Our chlorine then is going to be becoming kind of this inductive effect. So it's likely going to give up the proton due to the strength of that inductive effect. So the electron is being drawn away from the HO bond here. So it's being drawn away, and it's going to stay by the chlorine a little more. So again, a weaker base is going to give you a stronger acid. And you're talking about conjugate bases. Yeah. What? Strong acid, strong base reactions, you mean? Like when they're put together, that's just a neutralization reaction. So that's what I was talking about up here. So if you get a strong acid, strong base, you're going to form water because your pH is going to be 7. And then you form a neutral acid. So it's going to stay at 7. Because all of these are going to remain as ions. And all of this stuff is going to remain as ions. So carboxylic acids, all right. We have a acid functional group here that consists of carbon that's double bonded to an oxygen and a single bonded oxygen. So this is what that looks like, okay? We've got a carbon here. We've got our oxygen here. We've got a carbon that's single bonded to this oxygen, which is bonded to this hydrogen. The R then is going to remain the remainder of the molecule, which could be anything. So just don't worry about that, okay? But the idea is that your electrons are going to stay on this side, which makes it easier to pull this hydrogen away from it. Nitrogen bases, this is what those look like. You might, if you have taken biology recently, these words might look familiar to you. What are they? Huh? Not ATP, no. So yeah, they're your bases for your DNA. So the DNA is adenine, guanine, thymine, cytosine. And then when you're talking about RNA, the thymine gets replaced by uracil. Okay. All right, so we're looking at the difference in the pKa for acetic acid and fluoroacetic acid. So pKa of this guy is 4.76. Boy, that's spam. And this is going to be 2.59. Okay. So this hydrogen right here, if we were to pull this hydrogen away, why would it be easier to pull the hydrogen away from here? That means we have a higher concentration of H, which means we have a lower pH. Why would it be easier to pull the hydrogen away from here versus this guy? What's the difference between them? Can you tell the difference between these two structures? Huh? The fluorine, right. What do you know about fluorine? Right, it likes electrons. So it is going to be pulling those electrons over here, which makes it easier to pull this hydrogen away. Because this fluorine is so electronegative, this is going to stay as one part, and this is going to be easy to pull away. If we have more H's pulling away, then that means that we're going to have a lower pH. All right. In order to understand these, we need to draw the structures out. Okay, so there is my HNO2. And now I'm going to draw out my and my hydrogen's going to come off of here. All right, so if we think back to what I was talking about up here, about these oxygens, as we're adding more oxygens in, oxygens, other than fluorine, there's nothing more electronegative, okay? So as we are adding more of those oxygens in, which we've done here, it's going to be easier. This is going to be much more negative than this because we have that extra oxygen. It's going to be easier to pull that hydrogen away here. If we have a higher, if we have that being able to pull away, that's going to explain why we're able to have this as a strong acid and this is a weak acid. The oxygens are hogging this, the electrons. So the attraction for that hydrogen, remember remember that this is a covalent bond, right? Yeah. So if hydrogen donates its electron to that oxygen, then it's going to be H plus, right? You buy that? Okay. That oxygen here, because there's 3 of them, it's going to want that electron from hydrogen more than just these 2 oxygens. It's like an electron hog. It wants the oxygens. I still don't feel like I've gotten through to you. Just how I drew it.
But if the oxygen wants the electron more, it wants it blow away. I think, yeah, maybe.
Okay, let's talk again. Okay. I have nitrogen here with 2 oxygens attached to it. Yes? Okay. And wait a minute. This one should be, yeah, I'll have the hydrogen coming off this side this time. I got my hydrogen coming off of here. Okay. Now, this, I've got 2 oxygens here. Oxygen is highly electronegative. Okay. Which means it wants to capture the electron from this hydrogen. Okay. And pull it and have it as its own. If it does that, then this hydrogen's going to be free and floating free. And oxygen is hogged all of those electrons. Hydrogen doesn't have any more. Okay? Is that making sense? All right. When we have this, this is a weak acid. So that means that we have our pKa here is going to be 3.15, which means that we're not going to have that much of this happening. Okay, it's not going to happen as much as opposed to this guy. So over here, if I draw this one out, now I have that should be a double. Let's try it again. I have my oxygens here. I've got 3 of them. I have a hydrogen coming off of one of them. Okay. But again, this is an electron hog. These oxygens want that electron. So they're going to grab the electron from that hydrogen and hog it. And that's going to leave the hydrogen out here to float free. Because this is more of an electron hog, because there's 3 oxygens here, and there's only 2 here, there will be more of this happening, and you will have an increase, a greater amount of H pluses, because more of these are going to come off. Yeah.
Is there could it be like question mark test where we have to explain something like this?
Potentially.
Okay, because like, what could we say instead of like this wants it? Because I don't think
Electronegativity is very high.
Okay.
You're going to have an increased electronegativity due to more of these oxygens.
Yeah. Okay. That makes
Okay.
sense.
So because you have, it's like multiplying, making it more. Yeah.
Okay, so I know this isn't like correct, but can you like explain like why? So like if the oxygens are like negative and everything is positive, why aren't they like attracted to each other?
Because it's going to essentially be ripping off the electron from the hydrogen and say, you're not going to have an electron. I want it more. So as opposed to a sharing or an attraction, it's taking. Okay, it's just robbing that hydrogen of its electron and saying, no, you just go over there and you float around by yourself. I don't want you here. I just want your electron. Well, acids can be. Yep. Kick to the curb. Okay. So this happens with these highly electronegative elements. They just pull those electrons away. It's the best way that I can do to describe it. Okay. All right. Moving on. My God, I don't like that one. That one's rough on me. It's that highly theoretical stuff where you have to like start imagining things and it's icky. All right, moving on. This is better. This will flow better with you guys. Hopefully, yeah. All right. So, but you need this before you can do your lab next week. So we gotta talk through this. Okay. All right. So we've talked about our generic Ka equations here. Okay. Again, I really, really kind of relish the fact that we can just do A's here instead of having to write out all of those anions, especially for like acetic and different things that have like longer things. But this just gives you an easier way to set that up. Okay. So if we want to work with this, okay, if we take the negative log of the equation, we can end up with the P. This is just showing you how they are getting that equation that I talked to you about back in buffers. Okay, so they're just going through the fancy math of it all. Just realize that this exists. We've already talked about this. You're comfortable with this. You've been doing this with buffers, right? Okay. So the pH of the weak acid will be equal to the Ka. That's just going through this equation again. We've got that reaction here. If you were to add more strong acid, then that's going to take away from this guy. Again, we've talked about that. We're just trying to kind of go through that again. Now, when we're talking about indicators, so oftentimes, like back when you were doing your acid-base reaction in honors chem, I selected the indicator for you. I got you the phenolphthalein, okay? But you can use other indicators depending on where that equivalence point is. So for the phenolphthalein, where's phenolphthalein here? Is it even on here? There it is. Okay. So right here, phenolphthalein, honestly, you guys probably went just a scunch past that equivalence point when you were doing it, but to be able to get a visual, it works pretty well. So now there are other indicators though, because if you have, for example, something where you're taking a strong acid and a weak base, your equivalence point isn't going to be at 7 anymore. You're going to need an indicator that's going to give you where that value is. And so you have to be able to be comfortable picking out from a chart what indicator you would want to use. Okay. And most of the time, universal indicator isn't available to you. So universal indicator is essentially just a bunch of these put together. So it gives you kind of this rainbow color, which is kind of cool. This is also essentially what the pH paper is, not litmus, but pH paper, where they have, you can dip it down in and it'll give you a range of colors. They have essentially soaked the paper in that universal indicator. Okay. Now, you have to be able, from a chart, to be able to pick this out. So I'm going to show you how to do that. It's not a hard thing to do. The other thing that you need to be comfortable with, if they ask about, which I kind of doubt they will, but it's still good knowledge to have, is litmus paper. So litmus is a common one that they will use. You can actually create your own by using cabbage. Red cabbage. You can use that as an indicator. Somebody did that last year, I think, for their demo and at the end of the year. Used cabbage to create an indicator for pH. Maybe. All right. So what happens is, the way you remember this is, for acids, red will stay red if it's an acid. Okay. And blue will turn red if you have an acid. For bases will turn blue, or will turn red litmus paper blue, and the blue will stay blue if it's a base. So this is how you remember acids and base and litmus paper. So just so you're aware of that. Blue base. If you remember blue base, then it's easy. Okay. All right. So how do we figure this out? Well, what you do is you are going to look at your pKa, okay, of these different so you're going to look at the pKa of your acid or base, and then you're going to find the pH range where that base or acid changes. So if you look at the pKa of, say, do I have one here? Do I have an ad? Maybe it'll be down here. Okay, so pKa here, they gave us this 4.75. Okay, so that's our acetic acid. If we were looking at an indicator for that, we would want to find something in that range. So something in here that would be around 4.75 for its midpoint would be a good, so something in this range here would be a good indicator to choose for that. So if you find your pKa, if you know what that is, you have a range of a chart here, you just look for something kind of in the middle of that. So. All right. So again, the indicator is what you want at the steepest portion of your titration. So if you're given a graph, you would look to see where that pH is for that titration. And then you're going to try to find something with a pKa value similar to that pH value. That's it. Okay, so this Alizarin red is an acid-based indicator. It changes from pH of red at 4 and to yellow at 5.5. Okay, and these indicators will give you a different color depending on whether they are protonated or deprotonated. So whether they have a hydrogen attached to them or not. Okay, so an indicator will have one color when it looks like this. I'm going to do IN for indicator so you don't get it confused with HI, which is actually something. And then when it's in this form, it will have a different color. So for phenolphthalein, when phenolphthalein has an H attached to it, it has one color. And when it has no H attached to it, it has a different color. Okay. So we're trying to figure out, it's pH, it's red here at pH 4, and it's yellow here at 5.5. Okay. So would the protonated or deprotonated form be red? So as pH increases, H plus ions increase. No, as pH decreases. Bad lippy. Bad lippy. So pH goes down, H plus goes up. Okay. So would we have the H plus available here? We would have the indicator having more H plus attached to it because there would be more H pluses available for it to attach. So the protonated version would be red. Yep. Because those H's would be available to it to go with that indicator. Because there's more acid available. There's more H pluses available. Okay. And then if our pH is higher, we have fewer H pluses around. So then our indicator would be deprotonated, and that would be our deprotonated form. And that's going to be yellow. Whew. All right. So they want to know if it would be effective for sodium hydroxide with acetic acid, or would it be more effective with sodium hydroxide and hydrochloric? So which one would this work better for? Well, this pH is right in the middle of this, right? Okay. So it would be more effective for the acetic acid because remember, we want a pKa to be close to the range, which this is, of this. When we have these, what is its range? Where is it gonna, what pH is it gonna change at? Strong acid, strong base, equivalence point is 7. So this alizarin red would not be good for that because it would, by the time it's going to go through that equivalence point, it's going to be beyond the range of this. It would just stay yellow the whole time. Does that make sense?
Yeah.
Need me to talk it through again? Yeah? Okay. So remember I said that if you know the pKa, you want to find a pKa value for your, where the range is in between where that color change is going to happen. So the color change here happens between 4 and 5.5. Well, 4.75 is right in the middle of that range. You want the color change to happen when this is shifting from when it's getting neutralized. Okay. So this guy, by having a pKa of 4.75, it's going to get neutralized in that area. So you want a pH where that's going to happen. This, your strong acid, strong base, gets neutralized at 7. So that color shift, that color change is going to happen before you've actually hit that equivalence point. So when you hit the equivalence point, it's just going to stay yellow. It's not going to change at all. And you won't have any color indication of when that's going to happen. Now, for your lab, you're not using indicators at all. You're using a pH probe. And the pH probe is going to tell you when you are getting to the point where you're going to have that shift happen, because you're going to be watching the graph. And when that graph starts to really take off and starts to go vertical, that's going to be your equivalence point. All right. We have a pKa of nitrous acid. So this is a weak acid. It is 3.16. Buffer solution is made by mixing the acid with sodium nitrate. And we end up when bromothymol blue is added to the mixture, a blue color change can be observed. Which species is greater, the protonated or deprotonated at that point? Well, we know that blue is going to indicate that we have our blue can be okay, so bromothymol blue is going to be here. So when we have fewer hydrogens attached on available, then the indicator is going to be blue. So blue is going to be the deprotonated, because that would be available for this. So blue is going to be the NO2 minus. And whatever other color, what is the other color? Green for that one? Looks like a yellow, I guess. So yellow then would be your HNO2. So the deprotonated would be the blue color. And that's it.